Right, we want to look at another final solution, pH of a final solution question. Right, I said we are going to use this method, limiting. Right, now here I said this part here has to do with the excess reactant. So you first find out which one is the limiting reagent. Now you automatically will know what the excess reactant is. Then this information is about the excess reactant. You have to find the reacted number of moles by ratio. This one you get it by ratio, right? Then you have to find the initial number of moles of the excess reactant. Initial number of moles for the excess. Then you have to find the reacted number of moles. Then you have to find the number of moles that are in excess. We say Ne or N final. Then for the reacted number of moles, I will just use NR for the reacted number of moles. This reacted number of moles just more like your rice table. It's more like your rice table in KC. When you're doing KC, it's more like your rice sack table, right? It's more like your rice sack table. It's more like rice sack table, right? But where the E now here represents the excess in P. When you're calculating pH, it represents excess react. Then this is change, and change in number of moles actually represent the number of moles reacted, right? Yeah, it's the same thing. Initial is the same thing, but now in your rice sack, this one now represents your ratio, right? But in this case, it represents reacted moles by ratio. So it's actually still ratio, but reacted moles by ratio. That's what it represents, this one here. The first R. It is reacted moles by ratio. So I'm going to use ratio here to get the reacted moles. Then these ones will be the initial number of moles, Ni. This will be the reacted number of moles, which is still the same thing as the rice sack in Kc. And then E in this case remains excess number of moles, but in Kc it means equilibrium. Okay, then this one now is the what we call the concentration. And then in this concentration, yes, you're going to say the number of moles that are in excess now. The number of moles that are in excess divided by the total volume. So it's more like a rice sack, this thing here. Okay, so but the C now in this case is represented by the first C that is here, or you can say this first C that is here, because this chop part is for the chop part is for the pH of an acid. That one is the procedure for an acid, and then this one is the procedure for pH of a base. So, but it's more like a rice sack actually. Okay, right. It's just that now the notations are different. There's no equilibrium. We don't use equilibrium. We use excess number of moles, and then this one we use concentration. And this concentration now, you see the number of moles of that we get from the excess, divided by the total volume. Okay, so let's get into it and see how it works. So now in this case, now you are already given the pH of the final solution. So they say a learner, when we read the equation, they say a learner, right, adds the 150 cubic centimeter of sodium hydroxide solution of unknown concentration. So this one, you do not know the concentration. The concentration of this acid is not known, to a 200 cubic centimeter of a 3,03 mole per cubic decimeter of hydrochloric acid. So the concentration of hydrochloric acid is known, right? And the final, they find that the pH is what? Is 2. Remember, pH does not have units, right? And then we have the balance chemical equation given to us. Now, what is the information here? Right, I said we are going to use the method which says limiting what? We say limiting, right? Then it's either you chop or you cook. But let's check which one applies to us. This pH is less than, it's a pH that is less than what? 7, meaning this is a pH of an acid, right? So we are going to follow what? The chop. So, but then where are we starting? We are starting from the P, going backwards, right? Now, this pH, if the final pH of the solution is less than 7, it means the solution is acidic. It is what? Acidic. Meaning the acid was the one that was in excess. That's why we are having a what? A pH that is less than 7. Because this excess reactant here was the acid. So we already know that the acid was in excess. And the base was a what? A limiting reagent. So already we know this part. We are done with it. Right? But we're given the pH and all the stuff. But let's look at the question. What does it say? It says calculate the concentration of hydronium ions in the final solution. So what I'm going to do is, I know pH. Now, what am I going to do? I'm going to find what the concentration of hydronium ions are. What the concentration of hydronium ions are. Yeah. Because I know that this is concentration of hydronium ions. So starting from pH, starting from the back here, starting from pH, I'm going backwards like this, right? So let's look at it. We say, all right, the pH is equals to negative log concentration of hydronium ions. Okay, now we know what our pH is. That is 2. Negative log concentration of hydronium ions. To make the hydronium ion the subject of the formula, we say concentration of hydronium ions is equals to 10 to the power negative pH. But we know what our pH is. In this case, what is our pH? Our pH is 2. Right, you write mole per cubic decimeters. Right, and this is the same as 0,01 mole. per cubic decimeter. Per cubic decimeter. Right, we got the concentration of hydronium ions in this case. We are done. But when we are done now, but as we proceed, we are going backwards. For the next question, we will go backwards. We'll work this thing backwards like this. Okay? Because when you are given pH, it means you have to start from the pH. You go backwards this way. Right? You go backwards. So now, we now know that after this, I'm going to for the next question, I'm going to calculate the concentration. Okay? I'm going to calculate the concentration, and this concentration now that we calculate, it is concentration is equals to the number of moles that are in excess divided by the total volume. Okay, that concentration there, we know that it is what it is going to be. Concentration is equals to the number of moles that are in excess divided by the total volume. Right now, after gets so now from the concentration, after using the concentration formula, I will be able to get the number of moles. Yes, we will be able to get the number of moles here. Right. So let's get into it and see what happens then. So if you check now, we're going to say, right, already I have got the concentration of hydronium ions. Now to get the concentration of the acid itself, it's simple because I just use the ratio. I said to move from the acid to hydronium ions, you just use the ratio between them, between the acid. So the acid is to hydronium ions. What is the ratio? So you to know the ratio, you ask yourself how many hydrogens in the acid itself are there. There is only one hydrogen, so it means it is 1:1. Remember, hydronium ions are more like hydrogen ions. It's just like saying hydrogen ions. So in other words, here it's like I'm doing this. It's like I'm saying the ratio of hydrochloric acid is to hydrogen ions, right? So I say, okay, how many hydrogens are here? 1. And this is one acid, right? So we say this is 1:1. The hydronium ions are H plus. Their concentrations are the same. Okay, right? So, but then we decide to use hydronium ion because it's the one that is in the formula of pH. You won't forget because it's in the information sheet, right? So we say now, remember the pH formula. You can also say the pH formula is like this. You can also say it is like this. Concentration of hydrogen ion. It is also true if it's like this, but we copy the one that is in the information sheet, remember. Yeah. So there. Right, what is the ratio now? The ratio, we know the concentration of hydronium ions is that, and then the concentration of the acid itself, we now calculate it by ratio. If the ratio is 1:1, it means now the concentration of the acid and the hydronium ion is the same, right? So therefore it means that now the concentration of the acid is equals to 0.01 mole per cubic decimeter, right? Now I now want to get to this part now. I am done with this part. Remember, I'm saying I'm working backwards. I now want to get to this part here, right? So now, how is this related to concentration? You see, these two, how are they related now? This number of moles, and this concentration, how are they related? They are related via the formula that says C is equals to N over V, where now this is the concentration of the excess reactant, and the volume is the total volume. Okay, is the total volume then, right? Now the concentration, we got it, we said this is 0.01. The concentration is 0.01 is equals to number of moles that are in excess divided by the total volume. What is the total volume here? 150 plus 200 and plus 200. It means the total volume of this is 350 cubic centimeters, right? It's 350 cubic centimeters. Then that 350 you divide it by 1,000. The 350 divided by 1,000, so it becomes 0.35 decimeters. So we put 0.35. So that we can get the excess number of moles. Now you cross multiply. Right? So N now in excess is equals to 0.0035 mole. These are the number of moles that are in excess. Now, is it possible to get the reacted number of moles? I think the first one that you can be able to get easily is the initial before the reacted, because we have the initial information. We have information about the you see, we have got the concentration of hydrochloric acid and the volume, and that was what initially reacted right here. So I can use the volume of the acid and its concentration to get the initial number of moles. Then after getting the initial number of moles, that's when I can get the reacted number of moles. Remember, the excess reactant cannot be used in a ratio to get information about another substance. Even the initial number of moles cannot be used in a ratio to get information about another substance. It is only the reacted number of moles that can be used in a ratio to get information about another substance. Okay, that is the what we need to know. Okay, right. Now we got our excess reactant, we got the excess number of moles. Our excess number of moles, right? We remember we are working backwards. Okay, we're working backwards like this. Right. Remember that we are trying to get the initial number of moles of the NaOH, which is our base, and this base is a limiting reagent, right? And this information is only about the excess reactant. Remember, this is only about what the excess reactant. This is information about the excess reactant. not the limiting reagent. The limiting reagent will get information about it there. Right. After we got information here, all this information here, that's when we can go to the limiting reagent. Right. So let's work it out. I can get the initial number of moles before I can get the reacted number of moles, because I've got the initial information about the hydrochloric acid there. Right. Okay. So let's get into it and see what is happening there. Right. I'm going to say now C is equals to N over V. And this number of moles are initial number of moles for the hydrochloric acid, the excess reactant, right? Now, the concentration of the hydrochloric acid is what we have to, we already have it, 0.03. Then the initial number of moles we do not have. Then the volume is 200 of the acid alone. The initially, before it is mixed with anything, initially is 200 of the, right? You divide it by what? By 1,000. Then that is 0.2. So use 0.2. So the number of moles initial is equals to 0.006 mole of H what? HCl. And I said these are initial number of moles. But remember now that we say the initial number of moles is equals to the reacted moles plus the excess moles. All right. So now to get the reacted, you just take this to the other side. So now the reacted will be equals to I minus E will be equals to the reacted number of moles. Okay. So we're going to do that. Say, okay, the reacted number of moles is what? So we say NR is equals to the initial minus the excess, or minus the final, in other words. So this is equals to 0.006 minus 0.0035. Let's see. This is equals to 0.006 minus 0.0035, which will give us 0.0025. 25 mole of HCl. Right, these are the reacted number of moles. So we now know that we have the reacted number of moles, we have initial, and we also have that. Okay, we have that. Now I'm done with this part here. So where do we go when we're done with this part? Where do we go? Right, we are now targeting this. Right, now I'm now going to the reaction itself and say, okay, out of the number of moles that I have found, remember for the excess reactant I have found the 3 number of moles for the excess. I have the initial moles, I have the reacted moles, I have the excess number of moles. For what? For HCl. Now out of these 3 number of moles, it is only the reacted number of moles that I'm going to use in a ratio. So I said that the first R, it is the reacted number of moles in a ratio. You use them in a ratio. This first R, you use it in a ratio. Now, so it means I'm going to use a ratio. There. Let's see how we can do it. I'm going to say HCl is to NaOH. Now, the ratio is 1:1, as we can see from the balanced chemical equation, right? Now, we know the number of moles of HCl. It is 0.0, is it 0.025? Let's see. Right, I missed 1 0 there. I missed 1 0. There, 2.5. Then what are the number of moles? Okay, now if the ratio is 1:1, then it means the number of moles are the same, right? So the number of moles is equals to 0.0025 mole of what? NaOH. NaOH. Now, if I got the number of moles of NaOH and I also have the volume, then I can calculate the concentration, right? So I know that concentration is equals to number of moles divided by volume. I know the volume of NaOH, it is 150, right? So 150 divided by 1,000. 150 divided by 1,000. That 150 there is divided by 1,000. And it will give us 150 divided by 1,000. You get 0.15. Right, so going to say 0.0025. It's not clear here. We want the final answer now. And let me just do this. So the concentration is equals to number of moles divided by volume. And the number of moles is 0.0025. By volume is 0.1. The volume that we got is 0.1. And we get an answer of 0.017 mole per cubic decimeter of sodium hydroxide. So we were working backwards, right? So we worked backwards. There. So in summary, what we simply did here is this. We've done this, okay? We started from the pH, okay? Started from the pH. We got the concentration of hydronium ion. We got the concentration of the acid itself. Now, remember, the reason we are using CHOP is because the pH is less than 7, which means this pH is the pH of the acid, and the acid was in excess, right? It is meaning the acid is in excess because the reactant that is in excess is the one that determines the pH of the solution, if we remember, right? So I used the pH, then got there, then use this. Remember, this C here is concentration is equals to number of moles in excess divided by the total volume when they are mixed together. Now you get here to the excess number of moles. Remember, this is about the excess reactant there. Then I got initial number of moles using this initial information that we are given before I can get the reacted number of moles. Then I get the reacted number of moles. Now this reacted number of moles, I can use them in a ratio. Then still the same number of moles, but I use them in a ratio in the balanced chemical equation to get information about another substance. Right. So there become. All right, let's look at another question. What does it say, this one? They tell us that a beaker with 500 cubic centimeters sulfuric acid of unknown concentration is mixed with a beaker containing 300 cubic centimeter of 0.1 KOH, which is our acid, which is our base, right? They say the final solution in the beaker C has got a pH of 12. So we now have a pH of 12. Now pH of 12 means that the solution is basic. The solution is basic, meaning the base is the one that was in what? In excess. All right. This one you can also do it. Just try to attempt it before you see the solution. All right. Right. No, and as we read in beaker A, that's where we have got our acid, and our acid we don't know the concentration. Then in beaker in beaker B, we have got our base, and we know information about the base. All right, they mix them together, and then we get a certain we get our pH. Okay, right there. But from here we can conclude that the base is the one that was in excess because of the pH. Any pH that is greater than 7 is the pH of a base. All right. We know that the pH of a base is greater than 7. So this pH comes from a base, and the base is the one that determined the pH. And because we can see that value is the value of a pH of a base, not an acid. Okay, right. So what are we going to do? We're going to use limiting reagent. We're still going to use our procedure, our usual procedure, which is limiting reagent, right? But we don't chop in this case, we cook the base. we cook the base because that pH there is the pH of a base. Okay, that is the pH of a base. So we are going to start from the pH of the base and we go backwards. We start from the pH of the base and we go backwards like this. Right. So all this information that we get here, it's about KOH because KOH is our excess reactant. Okay, it's about KOH. Here is our KOH. Our KOH is our excess, whereas this is our limiting reagent. Yeah. Let's try to seize the information there. You can see this is what we're given. This is what we're given. Right. Then. Now, but let's look at the question. What does it say? It says determine the concentration of hydroxide ions in bicacine. Right? Now, where do I start? I'm starting from, because this is where you see this is hydroxide ions. This is where they are, hydroxide ions. So I must use what? I must start from the pH. We start from pH. There. I'm going to say, all right, the pH is equals to negative log concentration of hydronium ions. Now, the pH that I have is 12. Negative log concentration of hydronium ions. To make concentration of hydronium ions the subject of the formula, I'm going to say concentration of hydronium ions is equals to 10 to the power negative pH to the negative pH. But we already know what our pH is. That's 12. So it's to the power 12. We say now what? Mole per cubic decimeter. Don't forget to write units because this is concentration. Right? It means there are 12 zeros if you write here. So I can't write all the 12 zeros. So I decide to leave it in scientific notation. Okay? Now, where do we go now from here? I've got the concentration of hydronium ions. Now, the next thing is to go to a KW formula because we're going to backwards. So it says, our procedure says we must go to KW formula, which converts the concentration of hydronium ions to concentration of hydroxide ions. So when we go to our KW formula, what does it say? Okay. Going backwards. So it says KW is equals to concentration of hydronium ions multiplied by concentration of hydroxide ions is equals to 10 to the power negative 14. All right, then this is equals to concentration of hydronium ions was 10 to the power negative 12. write 10 to the negative 12 in circle brackets. When you substitute a value, use a circle bracket. In AOH is equal to 10 to the power negative 14. Then we are going to divide both sides now. We divide both sides by 10 to the power negative 12. Divide by 10 to the power negative 12, both sides. Right, so the answer that we're going to get is concentration of hydroxide ions is equals to 10 to the power 2, negative 2, which is equals to 0, 0, which is right, mole per cubic decimeter. Or you can write it in decimals. Say this is 0, 0.01 mole per cubic decimeter. That is the concentration of hydroxide ions in the beaker C. Now they want us to calculate the initial concentration of sulfuric acid. Now I'm still going to follow this. Okay, I continue. I'm going to try to find this one, the concentration of the KOH. Then after that, I come to this information, try to find the information until I get to the limiting reagent itself, the information about the limiting reagent, which is our sulfuric acid. You see? Until I get to the information of limiting reagent. Right. So let's get into it and see. Now, we are now answering the another question. Where do we go? I say, all right, KOH. Sorry. I'm saying KOH is to hydroxide ions. What is the ratio? So the question is, how many KOHs are here? Sorry, how many OH are here in this space? There's 1. So the ratio is 1:1. Right. Now, the concentration of hydroxide ions, we got it to be that. Now, what is the concentration of KOH? KOH. Okay, we want the concentration of KOH. So if the concentration, if you have got 1:1, so it means the concentration is equals to 0.00 0.01 mole per cubic decimeter of KOH. Okay, as well. Right, because of a ratio of 1:1. Now, or you can say you are cross multiplying. Okay, so now we got there. Where after this, where do we go? We must find the excess number of moles. Must find the excess number of moles. Now, to get the excess number of moles, what do we do? what do we do? So we say, all right, how is this one related? How are these two related? Because I just got this concentration there. How is it related to that excess, to those excess number of moles? We say concentration is equals to number of moles in excess divided by the total volume, the combined volume, right? So this is 0.01 is equals to number of moles that are in excess divided by the total volume. Is when you add 500 and 300, that will give us what, 800. Then that 800 you divide it by 1000, so that is in cubic decimeters, and you get 0.8 divided by 0.8. Then we multiply these two. What do we get? Let's see what we got there. So you're going to get number of moles is equals to 0.008 moles of KOH, obviously, which is our excess reactant. These number of moles that we got are the ones that are in excess. Okay, now I also have an initial information about KOH. This is our initial information about KOH. This one. This initial information, you have this information here. You can before it is mixed, right? Will give us the initial concentrate. It will give us the initial number of moles for the excess reactant, which is KOH, right? It will give us information. This one, there. So let's get into it and see. So we are going to say concentration, concentration is equals to number of moles that are initial divided by volume. Okay, now the concentration is 0.1 is equals to the initial number of moles are the ones that we do not know. Okay, then the volume is the 300 before it is mixed. The initial, it is before it is mixed, right? So that 300, you divide it by 1000, you get 0.3. So the initial number of moles now that you get, the initial number of moles that we get, what do we get for the initial number of moles? You're going to get 0.03 moles of KOH. All right, these are the initial number of moles for KOH. Now we can get the reacted number of moles. You know that the initial number of moles is equals to the reacted plus the excess. So to get the reacted, you just take the excess to the other side. You subtract initial and excess. So we're going to say now the number of moles that reacted is equals to the initial number of moles minus the excess number of moles, which is equals to the initial number of moles 0.03 minus 0.008. So 0.22 are the reacted number of moles. Let's see what we can do there. 0.2. So the reacted number of moles is equals to 0.0022 mole of KOH. Remember, this was 0.3. That's 0.03. All right. So we got 3 number of moles for the excess. For the excess reactant, we have our excess number of moles, right? We have our reacted now, our initial number of moles. We have got our reacted number of moles, which is represented by this part. Then it means now the reacted number of moles, I have to use them in a ratio now. We come to this R. This R is the reacted number of moles in a, you find, but if you use a ratio, you use them with a ratio, together with a ratio. This one's the first one. Must use them together with what? With a ratio, in a ratio. Okay, so let's see. We also got this one. We got this one, this number of moles. So we got all the 3 number of moles. The reacted. Now ours now is to now use. Remember we said we are going backwards. We are working backwards. We said we are working backwards like this. Right. So since I got 3 number of moles, out of this 3 number of moles of KOH, okay, I can only use the reacted number of moles to get information about sulfuric acid. It's only the reacted number of moles that you can use to get information about another substance. Okay, it's only the reacted number of moles. So now, what is the ratio now? So use them in a ratio. So we're going to say now sulfuric acid is to KOH. What is the ratio? According to the reaction, the coefficient here is 1 and there is 2. The coefficient is 2 there. We have got 2 as our coefficient. So the ratio is 1 is to 2 between the 2. Right, so 1 is to 2. Now, the number of moles that reacted for KOH is 0.022. The reacted number of moles. Now we want the number of moles of that. So you're going to cross multiply. Cross multiply there. Sorry, it's only how many there? It's two of them. I think we only have 1 0. We have 1 0 there. We only have 1 0 there. Okay. Then you divide now. So the number of moles will be equals to cross multiply 2, n is equals to 0,022. Then you divide both sides by 2. Divide by 2, divide by 2. Divide both sides by 2. What do you get? You divide, after dividing by 2, n is equals to 0,011 mole of sulfuric acid. Right, then once we got those number of moles, we can find out now what the concentration is. We can find out what the concentration is. So what are we going to see? So we say concentration is equals to number of moles divided by volume. And the number of moles is 0.011 divided by the volume is 500. That 500, the volume of sulfuric acid is 500. Then divided by 1,000, that 500. The volume there is 500, as we can see. Right? You divide that 500 cubic centimeters by 1,000, you get 0.5. 0.5. 0.5 there. So divide by it. Then we get a volume that is equals to 0.022 mole per cubic decimeter. Mole per cubic decimeter. Sulfuric acid. There. So that's how we dealt with this question. We can see when you are given pH, you work backwards. Like that. So it's either here you put chop or you put cook. You put cook if the pH is greater than 7, meaning the pH is of what? Of a base, because cook is for base. Then you put chop if the pH is less than 7. I mean, because the pH that is less than 7 is the pH of an acid, and acid will follow chop of an acid. Then this information is about the excess reactant. You get all the information about the excess reactant until now you get to the limiting reagent, the information about the limiting reagent. right? All right.